Okay, so good afternoon, everybody. I'm going to try to wrap this up a bit faster than what is written on the sheet. I'm just going to try. So just a little bit of update regarding the paper on the Chibougamau area. We've got a paper on the team's age that got published a few months ago, so if you're interested by that, just email me, I will send you a copy. And we've got a paper on the detrital zircon, the one that Pierre Baudot worked on, that we are going to try and get submitted this year. So that will wrap up the work of the Meteoros project in the Chibougamau area. So going back on this presentation, this relates to the papers for the SEG special issue. I'm only going to touch very quickly on the first paper, which was a comparison between the Wabigoon subprovince and the Abitibi subprovince. But I'm going to go in much more details on the papers on the Abitibi greenstone belt, just because there is more data, new data to show you, and because the Abitibi is such an interesting case study, well documented, you will see that when we look at intrusive rocks, there's a lot of things to say. So this is about intermediate to felsic, there it is. So this talk is about intermediate to felsic intrusive rocks only. This is the rock I've been focusing on to try and get as much information as I could out of this type of rock. The aim of this project was to look at the tectonomagmatic evolution of the greenstone belt. So again, that's why there was a Wabigoon and the Abitibi. There was a comparison between the two. But as you will see today, even if when we focused only on the Abitibi, there's a lot of interesting things to see, especially when you're tracking the extensional event and you want to date them, you want to locate them. Intermediate to felsic intrusive rocks are very useful. Okay, so a little bit of an introduction on this. How do we get intermediate to felsic magma? I will say felsic magma from now on. There is several ways you can do that. You can do partial melting of a mantle rock. I'm going to say melting from now on, but just understand it's partial melting. So you can get your mantle rock, your ultramafic rock, you melt it, and you get a mafic magma, and then you did a lot of differentiation, and especially fractional crystallization, that remains the most efficient process. You do a lot of fractionation, and you end up with a felsic magma. That happens a lot after the Alkean. In the Alkean, we've got a process that is still operating today, but that is very, very predominant in the Alkean, is that you do some anatexy. You melt a crystal rock. So that will get you, if you melt a mafic rock and your degree of partial melting is not crazy high, you will end up with a felsic magma straight away. And that's a very, very efficient way to produce a large amount of felsic magma, and that is, again, what is predominant in the Alkean. This is well known, so I'm going to give you the main type of magma we are producing, the one I've been working on, just as a reminder, but you all know them. First, you've got all kind of crystal melt, or of this anatexy melt. The main one would be the tonalite, derived from a mafic rock, so you get a basalt at depth with some water, you melt it, you end up with a tonalite. The other one will be the granodiorite, so the granodiorite, you get some tonalite gneiss at depth again. You melt it, you end up with a granodiorite. So this is to say that TTG are a suite, not a series. There is actually two different sources when you talk about a tonalite versus a granodiorite. And the last type of anatexy melt, it's more marginal. We are talking about lower volume of melt produced late in the evolution of the belt. This would be the perluminous magma. This would be the 2-mica granitoid, for example. So they derive from a sedimentary rock. And the rest of the name on these slides, they are the sanukitoids and they are the alkaline series. So the alkaline series, like in the Alkean and after the Alkean, it's still the same. You need an enriched mantle source. So there are two main types. They will be the mantle metasomatized by a fluid or a melt in some cases, or they will just be the primitive mantle, the undepleted mantle. So that's your enriched mantle source. You do low degree of partial melting and you get the alkaline series. The sanukitoid is a hybrid, so you need two different sources. What I'm going to show you in this talk is that when we focus on the Abitibi and we go into detail, we find a lot of hybrid melts, a hybrid city today. I will show you why I'm saying that, and that's why it's kind of a surprise to me. All of these end members they're actually intermediate cases, and there is a lot of them in the Abitibi. But I will get back on this during the talk. First, as promised, I'm going to touch on the first paper, the one that was comparing the Wabigoon and the Abitibi subprovince. In this paper, I use a very simple chemical classification, one that is using major element and some trace element to distinguish what is a tonalite, what is a granodiorite, etc. And the idea was to apply this on big data sets, so I could come up with percentage, how much tonalite is there in the Abitibi versus the Wabigoon, and that's mostly what this comparison rely on. And this will be the result of this comparison. I was able to show that there is more tonalite, let's say differently. The tonalite over granodiorite ratio is higher in the Abitibi compared to the Wabigoon. This just means that because the Wabigoon crust is older, it is more mature, it had more time to produce tonalite, and these tonalites then melted to produce granodiorite. This process went further in the Wabigoon because it's older compared to the Abitibi, and that, to me, is the main difference between the two belts. The Wabigoon was just older when the Kenorean series of orogeny started, and it was probably less able to produce the fluid fertile for gold and etc. So there is all kind of consequences to be a bit of a crust that is just a bit older when this Kenorean orogeny starts. But anyway, that's the first paper. As I say, I want to focus on the Abitibi today because there is so many things that came out of this work. So to finish the introduction, I like to highlight the main two stages of the evolution of greenstone belt, not just the Abitibi, using this diagram by Bikaus. I think we've all seen it. So the first stage, and these are magmatic stage, this will be the synvolcanic magmatic period. So that's a long period during which you produce a lot of mafic magma, so that will be the lava flow, the central volcano, or the layered intrusion. And at the same time, you produce a TTG suite. So that's the synvolcanic magmatic period. Then you got a transition period during which we produce a sanucitoid. But again, sanucitoid is an hybrid. It's just one among many hybrids. And I will show you why I'm saying that. And then we get into the syntectonic magmatic period during which you have the onset of alkaline magmatism. But that's not just that. You've got many other types of magmas that are produced at this time that tend to be more enriched in alkali compared to the magma produced during the synvolcanic magmatic period. And after that, once the deformation and mineralization once all of this is done, you've got a long stage during which you have a kind of thermal relaxation of your crust, and that's when you produce your two mica granitoids over a long period of time. And it's as if you, at this stage, you're only able to melt the sedimentary rocks, and which is a part of your crust that is easiest to melt. And that's what you get at the end. You've got a little bit of magma that is produced over a long period of time, just because you're melting whatever sedimentary rock there is left at depth in your crust. So that's a general picture, that's a general idea we have about the evolution of greenstone belt. And I'm going to conclude the introduction part of this talk showing you this map that is a bit old now. With what I'm going to show you today, this needs to be updated. But at least it shows in orange and most of the yellow here on the map, these are the intermediate to felsic intrusive rock that are being produced during the synvolcanic magmatic stage. So there is a lot of them, and already with a simple map like that, you can see that their distribution is uneven, it's heterogeneous. For example, you've got more of this intrusion here in the central part of the Abitibi. You got more of them in the eastern part of the Abitibi and the western side here as well, so along the edge of the Abitibi and in the central part. And if we look at the syntectonic intrusion, again, it's very uneven. You've got a lot in the south, in the northeast, a little bit in the northwest, not that many in the center. So there is all of these spatial variations that we are going to use now to reconstruct the tectonomagmatic evolution of the Abitibi. Okay, so let's focus on the Abitibi. So the methodology I've used for the Quebec side of the Abitibi, I've used a CGEOM dataset. And the main reason for focusing on the Abitibi is actually this dataset, because there is a lot of data, it's well organized. I've also got a very good quality map with the name of the intrusion. The geochronological data have been compiled as well in this dataset, so it's very useful to do that kind of work. For the Ontario side of things, I've used a Big House 2011 compilation, because again, you've got chemistry, age, and the name of the intrusion as well. And I've added 16 papers from the published literature to get more geochemical data in the mix. What I've been compiling for this work are the name of the intrusion, so I could compile their map, their extent on the map. The surface area of this intrusion is something I've used to draw my conclusion. I've also been compiling the geochronological data, so we could see the evolution of the type of magma being produced over time. And I've collected every geochemical sample that I could find within the mapped extent of all of this intrusion. So it's a bit of a brutal way to do it because, for example, you can tell me what about multi-phase Pluton? If there is an older phase with one geochemistry and a younger phase with a different chemistry, it will look like there is a complex magmatic event. It's true. In some cases, both have been dated, so I know it's different magma. In other cases, I may have concluded that these are hybrid just because there are two magma with different ages that overlap. That's one of the main limits of this work, but we have to live with it if we want to look at the scale of the Abitibi. What I've compiled are almost 160 intrusive suites, half of them with geochronological data, and with a very uneven distribution of the amount of data, of geochemical data I have per intrusion. Some are very oversampled, some are undersampled. Again, we have to live with that. But at least in most cases, I've got the rarest elements that are available. Okay, so let's jump into it. This is the data set, the complete data set shown on the Abitibi greenstone belt, on the map of the Abitibi greenstone belt. The color code you see is the one I'm going to use throughout this talk. It is the alkalic to calcic classification that you get when you use a sodium plus potassium minus calcium versus silica binary diagram. I'm going to show it later, but for those that are familiar with it, it differentiates the rocks that are enriched in alkali, the ones that contain more calcium than sodium plus potassium, and there is two intermediate categories. So that's what you see on this pie diagram, and on this map, the size of the pie diagram is dependent on the surface area of the intrusion, which is a proxy to the volume of magma being produced in a given place. So in a very general sense, when you look at this map, you see that the pie diagram with a lot of red rock, so the alkalic rocks, which many of them are from the alkaline theory, but you've got actually, it's not just the alkaline theory, it's more complicated than that. But if we look at their distribution, there is a lot of them in the south, a lot in the northeast, and not so much in the central part of the Abitibi. So that is something that came out of this work. You've all read paper about the Abitibi, with some of them talk about the north volcanic zone, the south volcanic zone. Well, when I look at this data set, and at least for the syntectonic magmatic period, it's more of a north, central, and south structure. For the synvolcanic stage, it's a bit different, but for the syntectonic stage, you really got three segments in the Abitibi with different magmatism. So this north and south volcanic zone, they don't really come out in this data set. It doesn't show. It shows more of a three segments type of things. Here I'm showing you exactly the same map, but this time I've got for each intrusion, I've extracted the polygon, and I give to each of these polygons, I gave the color of the dominant rock type. So for example, this one here, it is in dark blue because most of the rock I've compiled are calcic rocks. And this really highlight the volume difference that you get between what is in blue, so the calcic and almost calcic groups, which are the big batholith, these are the TTG suites. And it's very different from the A group, the alkalic group, which are the small plug in red here in the northeast and in the south of the map in most cases. The last intermediate group, the one in orange, there is actually a lot of variations. There's a lot of rock type in there, so I'm going to get back to it later on. To finish on the general idea, general things, general conclusion I want to draw from this data set, and before we jump on the details, I want to discuss this binary diagram. So especially this one here, you've got the age, the geochronological data, versus the northing parameter, so from the south will be here, the north will be here, and there is a pie diagram per intrusion. What you see here is a transition between the thin volcanic and the thin tectonic magmatic period. So when you've got a lot of calcic, the pie diagram in blue, this would be the thin volcanic stage. And when you transition towards the alkalic rock, that's the thin tectonic stage. And we see very well on these diagrams that this transition occurs earlier in the north, around 2700, and it could occur maybe 10 million years later in the south. So this is well known, but at least we show it again with this data set, and you see here the gap in central Abitibi. So again, during the thin tectonic magmatic period, there's already a north, a center, and a southern Abitibi. It's how it is structured. This one here shows you the age versus the surface area. So again, the TTG batholith are much bigger than the alkaline theory and other type of rock of the thin tectonic stage. And during the thin tectonic stage, if you want to get a big intrusion, you're usually within the intermediate classes. So you're not crazy enriched in alkali. If we look here, we are looking at the potassium over potassium plus sodium. So it's a potassium over sodium ratio, if I want to be more simple. So you got more potassium-enriched intrusion in the thin tectonic stage, but you still have some overlap. And if I look at the lanthanum parameter and the ytterbium parameter, so you've got some intrusions that are more enriched in light rare earth element during the thin tectonic stage, but this time we've got a lot of overlap between the two stages. And for the heavy rare earth element content, it's most of the intrusions are actually depleted in heavy rare earth element, whether you're during the thin volcanic or thin tectonic stage, and there are exceptions in the thin volcanic stage, which are the low pressure tonalite for most of them. And this here is just a lanthanum over ytterbium ratio. It's a fractionation of the rare earth profile, which is not so important for what we are doing today. Okay, so for the rest of the talk, I want to go into more detail. So first I'm going to talk about the calcic group, and I'm going to show you an example. I'm going to talk about the maps, the distribution. This is where we are going to get the most interesting conclusions out of this work. Then we are going to talk about the intermediate group a little bit and the alkalic group. So the calcic group, this is what it looks like. These are all the intrusions that fall into this general group. And here you have this same intrusion display on the ytterbium versus lanthanum binary diagram. So these are median value with error. The error is a standard deviation that is displayed on this diagram. In gray, it is a whole data set. In color, these are the calcic groups, the pie diagram for the calcic group, so one pie diagram per intrusion. So as you see, most of them are not very enriched in light rare earth element. No surprise, these are the TTG, these are actually, most of them are the tonalite. But there is a lot of variation in the content of heavy rare earth elements. So what I did, I produced 3 arbitrary groups, which are not that arbitrary. We know that there is the low pressure and high pressure TTG. So this is what you see here. The heavy rare earth element, the low heavy rare earth element group would be the TTG produced at high pressure. And the high heavy rare earth element group here will be produced at a much lower pressure. So this is well known, but what will be interesting, what is new in this work, would be to put everything in map view. So let's go. First, there are all these diagrams that I've used to conclude things on the petrogenesis of this intrusion. So I'm not going to go into much details for every intrusion. I'm just going to do it here quickly. Here you've got the sodium plus potassium minus calcium versus silica diagram. So you see all of them are in the calcic side of the diagram, and most of them are felsic. I will remind that the tonalite is defined, it's a felsic magma, the median value is 78% silica. So no surprise here. But you've got some in the intermediate area. That's because you've got some diorite that have been classified, they are part of the calcic group. So let me get rid of the diorite right away. You've got some here in the Chibougamau Pluton, but in the Chibougamau Pluton you've got more tonalite than diorite. That's why the Pluton fall into the low heavy rare earth element group here in blue. And you've got the Bourlamaque and the Chester intrusion, which are diorite dominated. That's why they fall in the intermediate heavy rare earth element group here on the map. So put aside the diorite, the rest of this intrusion are tonalite dominated. Let's talk about them because they give us insight into the pressure at which the partial melting occurred, and this is really what's important on this slide. So the first map here in blue, these are the high pressure tonalite. And if you look at their distribution, they are on the edge of the Abitibi here, on the edge here in the north, and you've got two here in the eastern part of the Abitibi. So the way I interpret that is that these are indicators of thicker crust in the Abitibi. They are the high pressure group. And to me, if you imagine that the Abitibi was a rift at first, you have the older craton, you rift it, you put all your mafic lava flow on central volcano within the rift. The edge of the rift will be where the crust is thicker. So it's not surprising to have the high pressure group at the edge of the Abitibi greenstone belt. Now this group is very interesting. This is the intermediate groups. These are the tonalite produced at a slightly lower pressure. And if you look at their distribution, there is some on the edge here, but most of them are here in central Abitibi along a north-south axis. So this is one of the main conclusions of this work. I wasn't expecting that. There seems to be a north-south axis along which the crust is thinner during the thin volcanic stage. So if we think about the Moho map we've seen before, there is no relationship between the two because we are looking at the oldest stage of the evolution of the Abitibi subprovince. And in this thin volcanic stage, there seems to be a north-south axis along which the crust was thinner than in the rest of the Abitibi, and along which you produce this intermediate group of tonalite. So I can't really explain it. This is just the observations that come out of this work. Last thing I'm going to say, if you pay attention at the age of this intrusion, there are some inherited zircons that are not shown here. There are some older phase, like there is a 2.8 gneiss, tonalite gneiss here in the Chibougamau area in the Anvil Pluton, which is probably from the older basement. But if you put that aside and you look at their age, most of this tonalite have been produced after 2725 or 2720. What this means, because 2720, we are pretty late in the thin volcanic magmatic stage. So what it means is that you need to rift your older basement, you need to get your lava flow going, your mafic lava flow, your thick mafic crust, you need it to be emplaced before it becomes thick enough and before you start getting the partial melting event going on inside the crust to produce the tonalite. So when you think about it, it makes sense. You need the mafic crust first before you extract the tonalite out of the mafic crust. But still, it's nice to see it shown by the data. So just a word of caution here, there could be a sampling bias. This intrusion has not been extensively dated, so what I'm saying now could be that we haven't dated the older tonalite, but for the moment, it gives us a nice logical story, what we've got. Okay, so the last group in the calcic group would be the heavy rare earth element undepleted tonalite, and they are shown on this map here in orange. They are a much smaller intrusion. Again, they are in the central part of the Abitibi along a north-south axis, so this reinforces the idea that during the thin volcanic stage, the crust was thinnest here in the central part of the Abitibi along this north-south axis. And if you look at their age, you've got a north to south migration of this type of magmatism. You've got the older one, 2721, in the Joutel area. And then you go south up to 2700 in the Blake River, where you've got that type of magmatism migrating from north to south. So here we are abandoning, in a way, the north-south orientation, and we are moving from toward an east-west type of orientation you're going to see in the thin tectonic period, in which it's older in the north, younger in the south. So again, this type of transition, I cannot really explain it, but that's what the data show us. Of course, you all know the name of these intrusions. They are, for most of them, related to VMS system, which again is not surprising. You've got low pressure partial melting, subvolcanic complex, so intrusion unplaced and differentiated at low pressure, so they are perfect to become the heat source of VMS mineralizing systems. Okay, so to conclude on the TTG suite, because in the last few slides, we've talked a lot about tonalite and a little bit about diorite. In this group, I'm going to talk about the granodiorite. So where do the granodiorite stand? They stand in the intermediate group on the alkali calcic and calc alkalic, meaning that they contain more alkali than your calcic group, which is normal for a granodiorite. And you've got here the list of Pluton. So this is a TTG-like subgroup, and what's interesting is to look at it in map view. So these are, for most of them, they are the batholith in which granodiorite are overrepresented, or they are the batholith in which granodiorite have been oversampled. I can't really tell which it is for most batholiths. And there are also some tonalite-bearing batholiths here, but with tonalites that are a bit more fractionated than the tonalite from the previous group. But whatever the explanation is, if you look at their distribution, again, they are along the edge of the Abitibi here and in the same area where we found the high-pressure group of tonalites on the previous map. So again, what it means, to get a granodiorite, you need to do some partial melting of tonalite source. How do you get more tonalite in your crust? Well, it could be the more mature part of your crust, or it could be just a part of your greenstone belt that overlay an older basement. That's another way to get tonalite in your crust and to be able to extract granodiorite melt out of this tonalite. So it's not surprising to find them along the edge of the Abitibi, because if you remember what I've said before, if it's a rifting where you expect to have older basement, where you expect to have more tonalite in your crust, is along the edge of the greenstone belt. Regarding the age of this intrusion, I'm not going to repeat what I've said before. It is the same story. I will just draw your attention on this here, the black stock and the Watabig intrusion. But especially the black stock, it's 2680. We are already in the sink tectonic period. So this granodiorite type of magmatism, it is, you produce a lot of granodiorite during the syn volcanic magmatic stage, but you keep producing them also during the syn tectonic stage. Okay, moving on, we're going to talk about the alkalic group now. So we are jumping on the other side of the spectrum. Within this alkalic group, you're going to have the alkaline series, but you're going also to have alkaline-like intrusion. And I will explain what I mean by that. So here on this diagram, again, ytterbium versus lanthanum, I've got all my pi diagram. And in order to facilitate the interpretation, I've come up with three subgroup, which would be the high heavy rare earth element subgroup, the high light rare earth element subgroup, and the rest of the data. Okay, so if we look at them again on this diagram, so on this one they are in the alkalic field, no problem. On this one, this is a source discrimination diagram, and you see that most of your data fall in the rock with mantle source, not surprising for the alkaline series, but many samples also fall on the side of the diagram for rocks with crustal source, which is a bit more surprising. On the sodium, on the potassium, sodium, calcium ternary, you see the different group I've come up with. The one in green, which is here, is more sodic than the one in red and pink, which are on this, which is on this map. And if you look at these last two diagrams, these again are source discrimination diagram. Most of these rocks, they've got potassium-bearing mafic rock as a source. It's a way to say it could be a mafic. Actually, this one is not perfect for mantle-derived magma. But you've got some rock falling, especially here in the field for TTG, and the red in the field for sanucitoid and alkaline magma. So what I'm trying to say here is that they are not pure alkaline melt. For most of them, they are actually hybrid between an alkaline melt and a tonalite melt. So again, what I mean by hybrid, it could be an older intrusion with a younger intrusion on top, but I'm telling you it's not the majority of the cases. In the majority of cases, hybrid means you had two different melts that got that mixed together, or you got a source that is complex that got two components. I'm going to just give you an example to get, if you got a mantle that is metasomatized by a tonalite melt, for example, you've got a complex source with two different components that are going to show in the final chemistry of your magma. Anyway, I can't, because I haven't done detailed work on individual intrusion, I can't tell you which is which, but I can tell you they are hybrid between the alkaline series, this type of melt derived from the mantle, and tonalite melt derived from mafic rock. So let's look at their distribution. You've got the one in red here. This one are the pure alkaline, if you want. These are really the alkaline series with no mixing, no hybridization, and very little fractionation. And if you look at their distribution, most of them are in southern Abitibi. So what does it mean? First, it's pure alkaline melt. We know that when you produce an alkaline melt, you produce low volume of it. So to get it into the upper crust, you need a crust that is able to canalize efficiently your magma. Also, this magma they show little evidence for differentiation, so this is going in the same direction. You need a process, you need a structure that is efficiently canalizing this magma through the crust. And these structures, they only exist in southern Abitibi. So this could be a major fault, it could be an efficient extensional event dated at 2682, 2683, if we look at the age of these intrusions. But this is what this intrusion tells us. Ideally, we will date all of this intrusion to get a better constraint on this extensional event, because if they all have the same age, then we have an extensional event that is very well constrained by this type of magmatism. Moving on, the one in pink here and the one in green, they are hybrid, so an alkaline melt mixed up with a little bit of tonalite melt, and you've got more tonalite melt involved for the intrusion in green here compared to the one in pink. So what's interesting about their distribution is that you have them also in southern Abitibi, but you also have them in northern Abitibi. So the way I interpret it, because they are hybrid, you have to think about processes that promote hybridization, and what could promote it would be an extension event that is not that efficient, that promotes the pounding, the stalling of the magma in your crust, so it can interact with other type of magma and hybridize and fractionate more, because you've got evidence of that in their chemistry. And this, in the north, that's all you get. You get an alkaline series that is this alkaline magma are being produced, but they have a hard time rising through the crust. And in many places, at many times in southern Abitibi, you have that as well. The magma has a hard time rising through the crust. That's how I interpret this data anyway. Okay, so for the last few types, we are first going to talk about the intermediate group that are alkaline-like. So what I mean by that, this rock, so first they are intermediate, they are alkali-rich, the alkali-rich subgroup. They are hybrid again. There is an alkaline melt that is involved, and it has mixed up with a larger amount of tonalite melt this time. So if we look at their distribution, this one, there is a lot of them in the north. So this is the same interpretation as before. In the north, it looks like your magma had a hard time rising through the crust, so we had more opportunity to hybridize, to melt, to mix with tonalite melt. Another consequence of that is that most of these intrusions, they are syntectonic intrusion, so it means that during the syntectonic magmatic period, you were still producing tonalite melt in the Abitibi. So we always think about the tonalite melt as being a synvolcanic stage magma. Well, this data set shows that tonalite melt are still being produced in small quantity during the syntectonic stage. That too, I wasn't expecting. And the third type of intermediate group, it is the same. It is whatever granitoid I had left at this stage. They fall in this category. And this, they are also hybrid between the alkaline melt and the tonalite melt, but with a much more predominant tonalite component in the mix. So these are getting closer and closer to the tonalite type. Some in the literature could be called enriched TTG. Maybe you've seen that in the publication of Jean-François Moyen, which would be almost a tonalite, but with a small enriched component in it. Again, a lot in the north, some in the south, small one, and there is usually there are small volume except for the Heber intrusion here, but Heber is not that well mapped, so maybe it is much smaller. The magma I'm talking about now is maybe much smaller than what is displayed on this map. And to conclude, the last type of intermediate rock in the intermediate group is the peraluminous subgroup. So this would be intrusions that are dominated by peraluminous rocks. These are your two mica granitoids that are produced after the syntectonic magmatic stage. So most of them, they fall into the alkali-calcic or calc-alkalic subgroup, except for the Bevcon that is actually falling in the calcic group. Bevcon is a bit of a weird one that I'm going to show you here in a minute. So first of all, let's look at their spatial distribution on their volume. The biggest of these peraluminous intrusions, they are in the south. So not surprising, this is a magma that need sedimentary rock at depth. The sedimentary rock are the source of this magma. So you produce a lot of this magma where you've got the largest amount of sedimentary rocks, so that will be in the Pontiac subprovince and next to it with the Lacorne, one phase of the Lacorne and the Lamotte intrusive suite. And as you get away from the Pontiac, you have very small intrusion, and interestingly, they are aligned along, more or less aligned along the Wedding-Lamarck corridor. So it could mean that this corridor was still active after the syntectonic period, and at this stage, at least within the Abitibi greenstone belt, you were only able to produce a little bit of melt where you could actually melt rocks, so where there was some sedimentary rock left. There is almost nothing that is known about this Grand Roi, Chicot, etc. intrusions, so I can't tell you much about this magmatism. The one in the south is better constrained. To conclude on this map, you have the Befcon and Duren intrusion here, so I'm just going to talk about them because they are a curiosity. They are in blue on this diagram. You've got a complete mixing line between the tonalite melt and a perluminous magma. So this, again, means that you still have tonalite melt that is produced very late in the evolution of the Abitibi, and in one case, at least, in this area, this tonalite melt mixed. This is a clearly mixing signal that you have in this ternary diagram here. This tonalite melt was able to mix with some perluminous magma. So I'm telling you, it's hybridization all over the place when you go into details into this data set. So to wrap it up, this is a conclusion diagram in which you see in the circle the magma we are used to. So for example, the tholeiitic series derived from high degree of partial melting of a mantle rock, tonalite derived from a mafic rock, granodiorite derived from a tonalite source, the two mica granitoid with a sedimentary source, and here the alkaline series derived from an unrich mantle rock, so the primitive mantle, for example, and derived from this mantle by low degree of partial melting. So that's what we know, what we are used to. What's interesting about this diagram is whatever is in between. These are all the hybrid. So the diorite, I didn't talk about this before because I talk a lot about it in the previous years. The diorite is an hybrid melt between the tonalite melt and the mantle-derived melt, a mafic melt. And between the alkaline series and the tonalite melt, that's where you got the greatest variety of melt. So you got probably, I would put the sanukitoid here, because when you read paper about the sanukitoid, many authors agree that they are hybrid between an enriched mantle source and something that looks a bit like a tonalite. So I will put them here, but sanukitoid is just one among many hybrid. Enriched TTGs that you see in the literature, they are probably closer to the tonalite side of this diagram, with a little bit of hybridization, and here you've got the other hybrid I've got in this work. The HKCA, I will put them here with a question mark. That's so a hybrid between a granodiorite melt and the alkaline series. And for the rest, in the Abitibi, the small intrusion like the Grand Roi Pluton, it could be a hybrid between a two mica granitoid and a tonalite melt. So a lot of hybridization, and now we have to wonder how we get so much hybridization in the Abitibi, because mixing to magma, if it's the type of hybridization we are dealing with here, it's not easy, especially when you get viscosity contrast and stuff like that going on. So is it just all about the mantle is hotter, the crust is hotter, so you can is warmer than today, so you can get this mixing process going on more easily, or is it just about complex sources? This are questions for later, for future work. So I will conclude with these two maps. So this is a synvolcanic magmatic period you have on this map here, with maybe an exception here, which is more of a syntectonic intrusion. And what you see in blue and green will be the high pressure or high pressure tonalite and the granodiorite. So those that need a thick crust that contains more tonalite gneiss than the rest of the crust you have in the Abitibi. And they are here in the east and west of the Abitibi. And you've got here this plug, this line of orange polygon with the intermediate tonalite, so the ones that indicate that the crust was thinner here, at least after 2720. And the one in dark orange are the small plugs that are heavy earth element undepleted that again point to lower pressure, so to a thinner crust along this north-south axis during the syntectonic period. And for the synvolcanic period. Now we are moving on to the syntectonic period. And what you see on this map, let's put aside the large volume intrusion in blue here. These are the perluminous magmas that are produced very late. But if I focus on the syntectonic period, you've got all of this pure alkaline series and alkaline-like intrusion in the south along this north-south axis, east-west axis, sorry. You've got a lot of them in the northeast along the Wedding, Lamarck, Cadillac, and in the Chibougamau area. And you don't have that many in the rest of the Abitibi. So it's really about the north, the center, and the south. And this is the structuration of the Abitibi that you get going on during the syntectonic stage. But during the synvolcanic stage, things seem to be different, at least from the orientation of this, for the distribution of the crustal thickness, things seem to be very, very different in the synvolcanic period compared to the syntectonic one. So a lot of small conclusions, things that I didn't expect, like this long duration of tonalite magmatism that is going on. It's starting late, around 27, 25 in the synvolcanic stage, but it drags on to the syntectonic stage, so that's something I wasn't expecting. I wasn't expecting to see that much hybridization, and again, if you have just one idea, take-home message, just remember that sanukitoid are just, it's a fancy name, but it's just one among many types of hybrid. There's actually much more of them, many of them in the Abitibi greenstone belts. And the heavy earth element content of tonalite was used to track the area of the crust that is thickest, so along the edge of the rift, and the area where it is thinnest, so along this north-south axis, right in the middle of the Abitibi. And if anyone has any idea how we get this north-south extensional area with more extension in central Abitibi, I would love to hear it. So thank you very much.